Okay, we are talking about graphs, and today we really will talk about graph representation. Let's see. Oh, there's a midterm 2 and programming assignment 2 review party on the 25th Wednesday. It's from 5 to 7 p.m. in Dempster 110. And then there's the programming assignment 3, and there's a final exam. So today's plan is ambitious. We're going to try to do graph representation and then talk about graph traversals, and we'll see how far we get. But before we start, we need to warm up. And so do you remember last time we talked about the handshaking theorem, which is just this theorem that says for simple graphs, if I sum up the degrees of the vertices in the graph, then that's equal to twice the number of edges, because you can count hands in the handshaking 2 ways. One, you can count the arms, and the other way is you can count 2 times the edges. So we had that theorem from last time, and so I have these 3 questions. Is there a simple graph whose vertices have degrees 1, 2, 3, 4, 5, 6, 7? Is there one that has another one that has vertices whose degrees are 3, 3, 3, 3, 3? And is there another one whose vertices have degree 2, 2, 2, 2, 3, 3? Got it?
Does it mean that every entity is a vertex and that has like example kind of 1, 3, 1?
Yeah. Yeah, I mean, just draw a graph and it'll have the number of vertices, which is equal to the number of numbers, and then each vertex will have the appropriate degree. Okay? I'll give you, I don't know, a minute, 2 minutes? Good question. These are simple graphs. A simple means, no self-loops, no multiple edges between 2 vertices, like A and B can't have more than 1 edge between them. Yeah.
One degree refers to the number of edges across the vertex.
Correct. The number of incident edges to the vertex. How many people would like a little bit more time? A little bit.
Oh, right. Yeah.
Okay. Is there one of these that is obviously not possible? I mean, really, really obviously not possible? Like really, really, really obviously? It's a simple graph. Yeah. Why? Why is the first one obviously not possible?
Because if you remove the 7 point, it's supposed to have a degree of 7. The 6 things it can connect to.
Yeah, the thing we could hope for, the most thing we can hope for is that it has an edge to every other vertex. I don't know why I'm drawing this on the degree sequence, but anyway, you get the picture. And that number is 6. So this can't be right because the degree 7 vertex can't exist in a simple graph. Okay, what about the second one? Not coincidentally, sorry, go.
I was just saying that, thinking that with the degree of some of the one is 15, but that's no way for odd numbers, so that's fine.
Yep, there's a reason why I put this on this page. It's because it's right below the handshaking theorem, and the handshaking theorem says if I sum up the degrees of the vertices, 3 plus 3 plus 3 plus 3 plus 3, which is 15, then that has to equal 2 times the number of edges. But 15 can't equal 2 times any number, at least not an integer. So this can't be done either. So this is a no, this is a no. And what does that mean? What is the generalization of this statement? I mean, you said when you sum up these vertices, the degrees of the vertices, it has to be an even number. So how is a quick way for you to tell if the graph that I give you as a degree sequence, how can you tell if that's a legal graph according to the handshaking theorem? What property does a graph have to have? I mean, it's true that it can't have 5 degree 3 vertices in it and all the rest even degree. Yep. Yeah, there has to be an even number. So every simple graph really, has an even number of odd degree vertices. That's the corollary from last time, the corollary to the handshaking theorem. So I thought it'd be nice to sort of see why it's a corollary, and it's because it follows directly from the handshaking theorem. If you sum up the degrees in a graph, and there's an odd number of odd degree ones, you're going to get an odd number. So that's not possible according to the handshaking theorem. What about the last one? It doesn't have an odd number of odd degree vertices. That's good. Yeah.
Could you draw
A pentagon and a triangle.
This is one of the vertices of the pentagon and one of the triangle trees.
You want me to draw a pentagon? Okay, let me draw a pentagon and a triangle. Together?
Yeah.
Okay, where does...
They share one.
They share one vertex. Oh, like this.
No, like, I mean, they share one edge.
Oh, like this. I think that works. Seem like we got 2 vertices of degree 3, and all of the rest are degree 2. And there's 1, 2, 3, 4, 5, 6 vertices, and there are 6 vertices there. Perfect. Great. Is there another one? Yep. Yep. So it's like a cycle. There's a cycle here of degree 2 vertices, and then you can add a chord. That's an edge that crosses a cycle. It's called a chord to that cycle. And you can add it in a couple of... Okay, so this is a yes. All right, great. So that's about counting edges and handshaking theorem. The next thing I want to talk about is this graph representation issue. So people have asked, well, it's a data structure. Graphs are a data structure. How do you represent them? And so there are two traditional ways of representing graphs, general graphs. One is called an adjacency matrix representation, and the other is called an adjacency list representation. And first we'll start with the adjacency matrix representation. And as you might expect, the representation involves a matrix, which is right here. And what you do is you put a 0 or a 1 in the matrix to indicate whether the edge that's indexed by the two indices of the matrix exists or not. So if I have an edge UV, then I put a 1 in entry AUV of the adjacency matrix. So here we have an edge from 0 to 1, so I put a 1 in 0, 1. That's this edge. And then I see there's also an edge from 0 to 2, so I'll put a 1 there. And then there's an edge from 1 to 2, and an edge from 2 to 1. And everywhere else is 0. That's the adjacency matrix representation for this graph. So I have a big, is that okay? Yeah.
We haven't touched on like instance matrices in this class. Does it have any relevance?
It's the same thing. Yep.
Oh, when we're filling in the adjacency matrix, it seems like the direction of the arrow determines like where we put the one within the matrix. Could you expand upon, like, I guess like the general orientation for this matrix?
Oh, I'm starting with the row numbers and then the column numbers. So if you want a directed graph like this directed graph that goes from 0 to 1, you want a directed edge from 0 to 1, then I think of 0 as being the row number and 1 as being the column number.
Also we're thinking in terms of right to left.
No? Oh, you mean the numbering of the matrix?
Yeah. Because like we didn't put a 1
In this location?
in column 0, row 1. Yeah. I'm just wondering why.
Because there's only an edge that goes from 0 to 1. There's not an edge that goes from 1 to 0.
Also, how do we know whether? So when we're like, so we're determining like which column to look at, which node are we looking at to determine that? Like, are we looking at the node on the starting end of the edge?
Are you asking about what a directed edge means?
No, I understand that, but I'm just wondering like how come for the edge from 0 to 1, we're putting the, like in the adjacency matrix, we're marking that down in row 0, column 1, instead of column 0, row 1. I'm just wondering, like, is there like a directionality?
You can do it the other way, if you'd like. I don't care. I mean, I do care, because I have to grade it if you do it wrong.
So, like, what's the convention, I guess?
That's the convention. Now, maybe answering the question in red will help you, but there was another question, yeah?
So, where the arrow starts is the row, where it ends is the column.
Correct. Oh, is that the question?
Yeah. It's like, what's the convention?
Oh, yeah.
Because
Okay,
otherwise
good.
it's ambiguous.
Okay, great. That's the convention. Okay, so what's the answer to the question in red? Got an undirected graph. What property does the matrix have? Now, in an undirected graph, I have an edge that's undirected, like the edge UV. That means I can go from U to V or V to U. So I would have two entries in the matrix that would be one for VU, one for UV. Do you know what that, if I have such a, yeah. Symmetric matrix, that's exactly right. So the graph that has this will be symmetric around the diagonal. If I looked at the matrix, then every time I have a 0 that's in this position, no, sorry, a 1 that's in this position, I'd have a 1 in the reflection cross, if I have it in IJ, then I'd also have 1 in JI. It's symmetric. Okay. Is it good? Runtime. So this structure is nice in some ways and it's not nice in other ways. So this representation of a graph will allow you to iterate over the vertices basically by just going down the rows. By the way, if you don't like your vertices to be numbered 0, 1, and 2, what would you do? If your vertices come in with names like elephant and rhinoceros and giraffe, what do? Yeah, use a dictionary. You know how to do dictionaries. There's like a bazillion dictionaries. You can choose one. Or you could just do lookup. To find out what the name of the node is, you look up the name using an array. Okay, how much time to iterate over the vertices? Iterate over the vertices means I have a for loop that wants to visit all the vertices and check that they're doing okay, or do something on them like print them. How much time will that take in this representation? Yeah. Yeah, the number of vertices. So, oh yeah, I forgot to tell you the parameters here. Yeah, let me tell you the parameters. We have graphs which have a set of vertices and they have a set of edges. And n is equal to the number of vertices and m is equal to the number of edges. And in order to iterate over the vertices, theta n. Now really there very well might be another array that tells you properties of the vertices, and you would just be iterating over an array. This isn't slowing you down at all. Iterating over the edges. If I wanted to find all of the edges and do something to them, like for example, I don't know, add a property to all of them, or maybe reverse them if I was in a directed graph. How much time would it take me to iterate over all the edges? Yeah. Yeah, this is the problem with the adjacency matrix. The adjacency matrix is a matrix, and in order to find all of the edges that are incident to a particular vertex, you have to check the entire row. And you're going to find a lot of zeros and a few ones, but you have to check the whole row to find the edges. So every cell of the matrix must be inspected. Or if it was an undirected graph, you'd only have to inspect half of the entries. But okay, yeah.
If we're just inspecting every cell, wouldn't it be old n again? Because it would be like iterating over all the vertices.
No, every cell of the matrix. This matrix is n by n. And you have to look in every cell. If you didn't look in every cell, I could hide an edge there, or not. And so you have to look. Iterating over vertices adjacent to a vertex. So I have a vertex, and I want to know who are my neighbors. I want to iterate over them. I want to say, tell my neighbor, I'm your parent, I'm your parent, I'm your parent, I'm your parent. Yeah. Theta of n. Even if that vertex doesn't have any neighbors, I have to look at all of the n cells of the matrix to know that. So this is really the reason. These two things are the sort of bad properties of the adjacency matrix. Iterating over adjacent things and iterating over edges, it's difficult, or it's slow. But this is the great part. How much time does it check to see whether a given edge exists? Like you want to know, I guess this is an adjacency matrix of friends, and you want to say, is person A a friend of person B? How much time does that take? Yeah, if you can do array lookups, it takes constant time. So, and that's pretty good. When you insert a vertex into this thing, sorry, just stretching or no? Oh, thank you. Brilliant. This is like we could have a fun. Yeah.
Would you mind saying White's constant time?
This is assuming that you can do a constant lookup in an array. So when you're in like a language like C++, the sort of assumption is that I can do a lookup. If I give you an index I and j, if I give you those two indices, you can look that up in constant time. Basically, you do a lookup for the row using I, and then you look up in that row vector for the position j, and both of those are constant time. At least that's the assumption in most models of computation that we're dealing with. Yeah.
Sorry, I'm still not sure why iterating over vertices adjacent to vertexes O and N.
Oh. So suppose that I ask you, what are the, I can't do this because I don't have a sheet of paper to do this, but suppose that I ask you, what are the vertices that are adjacent to 2? What are your eyes doing?
Looking at the edges. Like...
No. You don't have this. That's not what you have. You don't have that picture. You just have that matrix.
Yeah.
So what are your eyes doing when you find what are the vertices, what are the edges that are incident, or what are the vertices that are incident to a given vertex, like vertex 2?
Look at like top, left, right, bottom.
Well, here's the vertex 2 that I'm interested in, and this row of the matrix tells you everything that you can get to from 2. Okay? So your eyes probably should be going to that row and looking along that row to figure it out. But how long is that row? N. And you've got to look at the whole row. And by you, I mean a computer. Not you. Computer has to do this too. Yep.
Also, when you say that a vertex is adjacent, when vertices are adjacent to the vertex, it just means that we have edges starting from the vertex going to those vertices.
Correct.
Not vice versa.
Let's not worry about directed or undirected right now. But if I was talking about a directed graph, I would say, probably I would say adjacent to and adjacent from. But I would never do that to you. I would never do that. I would always be very explicit that I'm talking about what vertices you can get to from a vertex using a directed edge, which means you have to follow the direction of the edge. Or I would say, what vertices can you get to this vertex from following a direction? That's it. Yeah.
So to like iterate over versus adjacent, you just do like a lookup with 2 filled in. Okay.
Yeah, you just look up the vector indexed by 2, the row vector,
And then you just do.
and then you just for loop over that guy and see what's there. And then for every vertex that shows up, for every 1 that appears in that adjacency matrix, then that's the index of something that's an adjacent vertex to that vertex. What you're looking for. Yep.
Wait, what do you mean by like iterate over vertices? Just like people wander around in a row or like
No, I mean iterate over the vertices that are in the graph. So like if I wanted to color them all blue, then what I could do is go through, like there's an array representing all of the vertices in the graph. I could walk down that and change all the vertex colors to blue.
So it's not like from this matrix.
No, really it's not. It has nothing to do with that. Really. Okay. Inserting a vertex. That's what you have to do, right? If you want to insert a vertex, you have to add a new row and a new column, and you have to call it vertex n. All right, now you have 0 through n. How much time does it take to add this to a matrix? Yeah.
Would you put it in n squared because you have to resize the matrix?
Ah, excellent, excellent, excellent. So if you had to resize the matrix, you may have to resize it. And if you do resize the matrix, it will take you n squared time, and you would resize it to be about twice the size that it normally would be, and then you would get a bunch more ability to add vertices to this graph, and hopefully would pay for the cost of building this n squared thing. And amortized cost would be something like how much? Amortized cost for adding one vertex to this array. Yeah. Yeah, just n. So I think of this as being, when you insert a vertex, it's something like theta of n, except for resize. And resize, you have to be smart. So I'll just put down resize because you all are smart. Yep.
Well, if a vertex is self, is it adjacent to itself?
Yeah, you can put a 1 in the diagonal for self loops. Or if you have multiple self loops, you can put like the number of self loops in the diagonal. Is that what you're asking about?
So like if you told like the neighbors to change color, then it change its own color, it has to do itself.
Yeah. Yeah. Yeah.
When you're inserting the vertex, you add the column and the row. Wouldn't it be n close to n squared?
Well, the number of entries that I have to enter is how many? The number of new cells that I add to the matrix is how many? About. Yeah. 1, 2, 3, 4, 5.
So that's close to n.
That's 2 times n, something like that. And I'm just saying that if you don't have to rebuild the thing, if you don't have to make space for a new one, then you can just fill in that with all of the zeros and ones that you want to fill it in with, and it takes time, basically theta of n. Yeah.
When you insert a new vertex, how can you structure the array originally so that you don't have to shift everything over? Everything that's already in the matrix.
You mean you don't want to use a vector of vectors? I don't have to shift anything on the vector of vectors. I just have to add stuff on the ends. And then add a new vector. Right? If you wanted to put it at the beginning, then we would have to talk.
Because the wording of n times n array A implies that it's one array.
It is one array. One array. But how do you implement an array in C++? I mean, there's multiple ways to do it. You can implement it as a block of memory that you've happened to partition up into, but you could also use a vector of vectors. I'm adopting the vector of vector approach. Yep.
What you're saying is like theta of n without resize, but even with resize, it's amortized still theta of n?
Yeah. These are all great questions. I love this course. How much memory does this take? Come on. We got to move on here. Memory. How much memory? Space. There you go. We're storing bits in a matrix, so we have theta n squared bits. You can actually store other stuff in there too. You can store lots of things, but appropriate to the particular edge that you're storing it for. So you can add edge attributes easily in an adjacency matrix as well. Okay, great. Let's not scribble out the graph. So now the other option is adjacency list representation. Now in an adjacency list, as you might imagine, there are a bunch of lists. And the lists are indexed by vertex. So L of U, which is the list associated with vertex U, contains vertex v if and only if uv is an edge of the graph. So we can do that for this guy. We can say 0 has an edge that goes to 1. So there'll be a linked list here. I'm making it a linked list because I like linked lists. And the other thing that it's going to is also a 2. And then there's a null at the end. And 1 has an arrow that goes to 2. So there's an element 2 in its linked list. And 2 has an arrow that goes to 1 in the graph. So it has a 1 in the linked list representation. And nobody points to 0. Interesting. Okay, so there's a linked list representation. Again, if you want to iterate over vertices, you have this nice array here which stores the head of the linked list, but could also store properties of the vertex. It could store things like its name or its color or whatever you'd like. So iterating over the vertices is theta of n again. How much time does it take to iterate over the edges in the graph? All of the edges. Remember, we have 2 parameters describing our graph. One of those is n, which is the number of vertices. The other one is m, which is the number of edges. How much time does it take to iterate over edges in this representation? I want to visit all the edges. Theta of m? What if there were no edges in the graph? Yeah. M times n?
Yeah.
Yeah. Who said that? Plus. I think you mean plus. So if you wanted to hit all the edges, you have to visit all the vertices to find out if they have edges. So there's n work there. And then the work you do walking down the linked lists, that work is associated with the edges that are in the graph. So its total amount of work is n plus m. Yep.
What do you the linked list store? Like for example, 0 stores 1. Is that like a pointer back to 1? Or?
Oh, this is like the name of the node or the index of the node that you would store in that structure. So the structure would have, it would be like a regular linked list structure, which would have a pointer to the next thing in the linked list. And that's what I'm drawing here is this kind of a pointer thing. The edges in my structure are pointers.
But then if you looked at from that 1, would it bring you to index 1?
Yeah, so you could take this and use this to index into your array to get down to 1. So you can follow edges by pick up the index out of the structure, go into the array to that index location, and then you can march down the... Okay, how much time does it take to iterate over the vertices that are adjacent to a given vertex? Let's call this vertex U. How much time does it take to do this? Yep. Yep. So the time to iterate over the vertices that are adjacent is the time it takes you to walk down the linked list. So it would be... Now, in this particular directed example, you might be interested in not just the edges that you can take away from the vertex, leaving vertex U, but you might also be interested in the edges that can come into U. Then you might build another linked list for the incoming edges. This is sort of the linked list for the outgoing edges. So you could have what did I call this? I called this something. No idea. Oh, I see what I did. Maybe keep a list for in edges and out edges. maybe it'd be useful to know what things can come to you as in addition to the things that you can get to. So this representation that I've drawn here is really the one which is an out edge representation. So it's the edge going out from a vertex that's stored. But you could store another one for in edges. And in an undirected graph, you would just have every vertex would have, if I had an edge A, B, both A and B would have each other in their lists, their adjacency lists. Okay, so it's something like the order, the degree of the vertex. And what about checking whether an edge exists? How much time does that take? If I ask you, does the edge UV exist in this graph? How much time would that take? Yeah. Yeah, it's something like either the degree of U or the degree of V, depending on whether you're talking about an undirected graph or a directed graph, or depending on whether you're talking about in edges or out edges or however you want to do it. But it's something like the degree of U, or it could be the degree of V. This is depending on whether, what I just said. Sometimes you can get the minimum of the degree of U and the degree of V because you can store the actual number of adjacent vertices, the degree. You can store it with the vertex. So you can just look in there and it says, vertex U has degree 27. Vertex V has degree 3. Checking for the edge UV, you would go down the one that has degree 3. You get the minimum of those two. So you could get the min of those. If you store the degree in the vertex array. Is my handwriting degenerating? Are you just going with it, but you're really upset? No? Yeah.
You mean like store degree as like a field in like each row?
Yeah, right here. You could store like this one has degree 2, this one has degree 1, this one has degree 1.
Like there's a node class.
Yeah, yeah.
Wait, and then so which one corresponds to which like header graph, like undirected and directed?
This works for undirected or directed.
I mean like the runtime.
All of the runtimes. Oh, you mean in terms of the degree?
Yeah.
Oh, well, it depends on if you want in edges or out edges. But if you were looking for out edges and this was an out edge representation, then it would take you a degree of U to figure out if there's an out edge from U. If you're in an undirected graph, then it would be whatever, degree of U or degree of V, depending on which one you look at. And if you keep that number, then you can get minimum of degree U and degree V. Yeah.
So like, since this is a directed graph, degree means like edges going out of the.
Yeah, I'm talking about out degree here for this particular representation because I'm looking at an out edge representation. But there are people that when they look at a directed graph and they see edges coming in, they count them. And they see edges going out and they count them. So the total degree for a vertex in a directed graph could be either out degree, in degree, or the sum of both.
Oh, but
It depends on who you're talking to.
Right, but for this runtime, it's just out degree, right?
Yeah,
Oh, okay.
for this directed out degree representation. And usually, I have to tell you, people usually say out degree of a vertex, or in degree of a vertex, or degree of a vertex when it's like an undirected graph. So it's not so Wild West as I'm portraying it.
Oh, I see.
Okay, how much time does it take to insert a vertex into this graph? Got a vertex, and it has, like, let's say, some number of neighbors, and I want to insert it in there. Theta of, yeah. Yeah, what's that? What's the length of the linked list?
Degree?
Yeah. What are we going to call the new vertex? X. So let's say to the degree of X. Except when...
Why can't it be 1? So you can just insert it from.
No, this is a new vertex.
Oh.
You gotta make a linked list for the new vertex. Except it's going to take more time when... This is your cue. It's going to take more time when you resize. Good. How much memory does this take? Yeah. Yep. There's n, and then there's m. N for the array of vertex pointers, the vertex data, and then m for each of the links in the linked lists. Yep.
Is there to add all the incoming edges to that degree as well? When you go through all the vertices?
How much time does that take?
You don't need to go to the ones that
If it's an undirected graph and I add the new row, or let's not call it a row, let's call it the new entry at the bottom with the degree of x new things in it, how much time does it take me to create, for this undirected graph, I have to put in entries into the other linked list. How much time does it take me to do that? Again, degree of x, because I have to go up and index to the new place, put it into probably the front, do the whole deal. So it's still degree of x. Okay? Yeah.
So like for that question, you mean just like put the new entry on the front of the list, like so you don't have to go over it?
Sure. Why not? Yeah.
Well, just for clarification. Also, when we are inserting the vertex, are we inserting the vertex into an existing linked list, or are we extending the array?
No, we're adding a new vertex. You have to extend the array. You're adding a new vertex to the graph.
Oh, then wouldn't it be theta of n in this case?
No. No, how much work do I have to do to add that new entry to the array? Constant to add a new entry, and then I have to add its linked list. How long is this linked list?
Adding to the array is constant. Oh, because we just added to the end.
Yeah, unless there's a resize.
Oh, I see.
Not everybody's keeping up here. We gotta get going. Yep.
Where I just don't really get why it's like or theta degree v.
Oh, it depends on which one you look at. Like if you're in a undirected graph and you're asked if the edge UV exists, you can either look up U and try to find V, or you can look up V and try to find U.
Okay, yes.
So either one works. And if you happen to store the length of the linked list, or the degree of the vertex, then you can be wise about your choice and pick the one which is smaller.
What about like very directed graph?
Well then, again, if you have an in-degree representation and an out-degree representation, you can either do it from V's point of view or from U's point of view. Weighted graphs. We have no time. Graphs. Let me tell you the story about this picture, though. Do you see this picture? What do you think this picture is? It says Black Sea at the bottom. It says Baltic Sea up there, so now you know where it is. It's got a bunch of numbers in there. It's labeled secret. It looks like it's from about the 1950s, something like that, which it is. What do you think it is? Railways. Railways in Russia. The part of Russia that butts up against Europe. Why would people be worried about railroads in Russia in the 1950s butting up against Europe? Well, they were worried about communist invasion. The people that were worried were the people in the United States, who really shouldn't have worried at all. But in any case, that's what they were worrying about. And so one of the first This is a graph that was used to decide where the Air Force should bomb to shut down the transport of supplies from the interior of Russia to the Western Front in case of a war. It's the RAND Corporation. And this was done, they figured out what's this cut right here, that dotted line that goes through there, that's the ones that they would bomb. It was optimal bombing, meaning they figured out the fewest number of bombs to drop to cut the supplies from the east to the west. It's a network flow problem that you'll learn about in 420, if you take 420. But it's kind of creepy, actually. So let's move on. Oh, I guess the point of this was that every edge had a weight associated with it, which was sort of the cost to bomb it, or something like that. Actually, what it was it's the amount of material that was traveling on that edge. And anyway, let's move on. Oh, yeah, I have two questions at the bottom. Where would you store this information about weights in an adjacency matrix? I think that's pretty obvious. You would store it in the adjacency matrix in some sort of object. So every edge cell would have an additional field in it. And then the other thing is, where would you store it in an adjacency list? That also seems to me pretty obvious. It would be in the linked list, in the nodes in the linked list, right? Anyway, creepy. Not something to think about before going to sleep. Okay, now I want to talk about traversals. You know what's really nice about this? It's really nice that you've actually done a programming assignment where you did both breadth first search and depth first search already. So basically, I don't have to say anything. I can just zip through these slides and you will be happy because you know it all already. Breadth first search uses a queue. If I wanted to visit the vertices of a graph in breadth first search order, I have to start someplace. So let's suppose that I start at vertex A. Breadth first search, what does it do? It throws all of the vertices that I can get to along one edge from A into the queue. So it starts off, it actually started off with A in the queue. It dequeued it, and it said, what can I get to in one step from A? And it said, I can get to B, C. By the way, this is the front of my queue, if you were wondering. B, C, E, F. That's it. B, C, E, F. Those are the only things that I can get to in one edge from A. And I record the fact that I can get to them by one edge, like this. And now these are all in the queue. And then I pull the next thing off of the queue. I dequeue the next thing, which is B. So in some sense, A was responsible for all of these to be in the queue. A was the parent of these nodes being in the queue. Now I go and pull B off. B gets removed. I can get to C, C has already been marked. I can get to D. So D goes into the queue along that edge. And B was responsible for putting D in the queue. And then we keep going. And we pull C off, but C is surrounded by things that have already been in queue. We can pull E off. E is surrounded by things that have been queued except for one, G. So G goes into the queue. Who's responsible for G being in the queue? Thank you. E. Now we keep going. F gets pulled off next. F has one vertex H that has not been previously visited. It gets put into the queue. And then basically after that, everything just gets pulled off the queue. This thing that I've drawn here, these dark edges in blue, that's called the breadth first search tree, the BFS tree of this graph starting from the vertex A. You might ask, if I change the order in which I visited the vertices, if I changed the order in which I pushed the vertices into the queue, I would get a different tree, and the answer is yes, you would. So somebody has to tell you to follow alphabetical order or something like that if you wanted to construct one, or you could just do it. We just followed the adjacency list representation and walked down the list. Okay, that's breadth first search. Unbelievable. Any questions? Okay, I will see you on Monday.